Have you ever sat down to learn something new only to feel completely overwhelmed within minutes? Maybe it was a math problem with too many steps, a lecture packed with unfamiliar words, or an app with so many buttons you didn't know where to look. That feeling has a name. It's called cognitive overload, and understanding why it happens can completely change the way you learn, teach, or design anything meant to be understood. This idea comes from a framework called cognitive load theory. It was developed by educational psychologist John Sweller in the late 1980s, while he was studying how people solve problems. He noticed something strange. Learners who were given open-ended problems to solve on their own often struggled far more than learners who were simply shown how a problem had already been solved. That observation eventually grew into one of the most influential ideas in how we think about learning today, and it has since been tested, refined, and applied across classrooms, workplaces, and digital design for decades. The theory starts with a simple but powerful idea about memory. Our brains have two main types of memory involved in learning. The first is working memory. This is where we hold and actively process information right now in this moment. The second is long-term memory. This is where knowledge is stored permanently, organized into patterns called schemas. Here's the catch. Working memory is incredibly limited. Most research suggests we can only hold around 4 to 7 pieces of information at once, and only for a matter of seconds unless we actively rehearse it. Long-term memory, on the other hand, is essentially unlimited. It can store a lifetime of knowledge and experience. Learning happens when information successfully moves from that fragile, limited working memory into the vast, stable storage of long-term memory. But if working memory becomes overloaded, that transfer breaks down. The information gets lost before it ever has a chance to stick. This is cognitive load. It's the total amount of mental effort being used in working memory at any given time. Before we get into the types of load, it helps to understand one more concept called element interactivity. Some pieces of information can be learned in isolation, without needing to think about anything else at the same time. Other pieces of information only make sense when several elements are considered together, all at once. Learning the vocabulary word for apple in a new language is low in element interactivity. You can learn it on its own. Learning to drive a car in heavy traffic is extremely high in element interactivity because you have to track your speed, the cars around you, the traffic signals, and your steering all simultaneously. The more elements that must be held in mind together, the heavier the load on working memory, even before we consider anything else about the task. With that foundation in place, Sweller identified 3 distinct types of cognitive load, and understanding the difference between them is the key to using this theory well. The first type is intrinsic load. This is the mental effort required by the actual difficulty of the material itself. Learning to add single-digit numbers has low intrinsic load. Learning to solve a system of differential equations has high intrinsic load. This type of difficulty is built into the subject matter. It can be managed by breaking complex information into smaller chunks, but it can't be eliminated entirely because some things are simply more complex than others. The second type is extraneous load. This is the mental effort wasted on how information is presented, rather than the information itself. This is the load we most want to reduce. Imagine a slide covered in cluttered text, confusing diagrams, or a narrator describing an image while unrelated text scrolls across the screen at the same time. None of that extra effort is helping the learner understand the actual concept. It's just noise competing for the same limited mental space. Poor design creates extraneous load, and good design eliminates it. The third type is germane load. This is the productive mental effort that directly contributes to learning. It's the work of connecting new information to existing knowledge, building long-term memory schemas we talked about earlier. Germane load is good. It's the effort that actually builds understanding. The goal of good instructional design isn't to eliminate all mental effort. It's to strip away the extraneous load so there's more room for germane load to do its work. So what does this actually look like in practice? Cognitive load theory has led to several well-known learning strategies. One is the worked example effect. Research shows that beginners often learn better by studying fully solved examples first, rather than immediately attempting to solve problems on their own. Watching a complete solution reduces the mental strain of both learning a new process and executing it at the same time. Another is the split attention effect. If a learner has to look back and forth between two separate sources, like a diagram in one place and its explanation in another, that constant mental juggling creates extraneous load. Integrating related information into a single, unified location makes learning far more efficient. There's also the redundancy effect. This one surprises people. You'd think hearing narration while also reading identical text on screen would reinforce learning. Instead, it often does the opposite. Processing the same information through two channels at once can overload working memory rather than support it. And then there's the modality effect, which suggests that combining spoken narration with visual images tends to work better than combining written text with the same images. This is because speech and visuals use two separate processing channels in the mind, spreading the mental load instead of concentrating it in one place. There's one more twist that makes all of this more interesting, called the expertise reversal effect. Many of these strategies are incredibly helpful for beginners, but they can actually backfire once someone becomes more experienced. A worked example that guides a beginner step by step might feel slow and even mildly annoying to someone who already knows the material well. Their long-term memory already holds the relevant schemas. So extra guidance stops being helpful support and starts becoming unnecessary clutter, adding load rather than removing it. This is why good instructional design often needs to adapt as a learner's skill level grows, rather than using the exact same approach for everyone at every stage. Researchers have also spent a lot of effort figuring out how to measure cognitive load in the first place. Some studies simply ask learners to rate how much mental effort a task required, on a simple numbered scale, right after completing it. Others look at how long someone takes to respond to a secondary task while learning, on the idea that a full working memory reacts more slowly to anything else competing for attention. None of these methods are perfect on their own, but together they've helped confirm that cognitive load is a real, measurable phenomenon and not just a helpful metaphor. Cognitive load theory matters far beyond the classroom. It shapes how software interfaces are designed, how training manuals are written, how safety instructions are formatted, and even how video tutorials are structured. A pilot's emergency checklist is built around this theory, since a panicked mind under pressure has very little spare working memory to work with. A well-designed phone app hides advanced settings behind simple menus, so a new user isn't confronted with everything at once. Even a well-made recipe video, showing one step at a time instead of listing every ingredient and instruction on a single crowded screen, is applying these same principles, whether or not its creator has ever heard the term cognitive load. Anytime information needs to move from a screen or a voice into a person's understanding, this theory is quietly at work in the background. The next time you find a tutorial confusing or a presentation clear and easy to follow, there's a good chance cognitive load explains the difference. It's not always about how smart the learner is. Often, it's about how thoughtfully the information was designed. When we respect the limits of working memory and give the mind room to build real understanding, learning stops feeling like a struggle and starts feeling like it simply makes sense.